to begin with, they're going to start by perhaps cleaning up some code. Right, so there's a lot of redundant code. So let's see how we can simplify the logic. We're not using this one anymore, so we can remove this, and let's move our import statements above. So let's move all of that above, and then let's do this. And let's get the run simulation out. And let's remove the portfolio also. Later we can see how that works. So we can remove the portfolio. And we don't need this for now, so later we might rewrite the code, but for now we don't need it, so let's just remove it. Okay. So actually one thing I wanted to add was that there is some redundancy in some of the logic, and we want to make it as simple as possible. So to begin with, we will just go into the main file, and let's try to see how long our operations take. Say maybe for just 200 tickers. So we're just testing. Can do test for. So in order to make our code run faster, we're just going to do this, right? And then we're going to run this, and let's run the simulations. We can do this. And this is the same as going into the code. Okay, we could do this, or basically, we can go inside the util file and just, I guess, do this. So actually, we can just do this. We don't have to do all of that. So that's okay. Let's just do it inside the main utility file. Okay, and this is our code. So let's run this. Let's make this run a little bit. Let's clean this up a little bit. So okay, let's do that here. Run the main function. That's good. And then we want to say do something like just capital dot list. I'm going to print the last terminal capital. So let's do this. And then let's print it after each simulation. So let's see how long this will take. All right, it should take us quite long. So we're just gonna ignore all the print statements, and let's try to run this code and see how long it takes. Well, out of a total of done. So out of a total of should be close to 500 tickers. We're just doing 200, right? So let's see how long this will take for us to get the result, and we will proceed with showing the optimization. We finished running the whole code, and you can see that it took about 6 minutes in total, which is not too bad, but it could be a lot worse. Anyway, so let's just copy this benchmark and then run here. So let's take this. Let's Control-C, Control-V, and this will be what we want to compare to. And we have 6 minutes. And you might think, okay, that's not too bad, but it could get a lot worse, okay? For example, if you check this post, you can just Google flirting with CPUs, and you'll see that we have a paper for you to download, right? You can just download it here, no problem. And then this is the paper. You can get run times up to even 20 minutes or so, which is really very long, right? So here we have 20 minutes of runtime, and we can improve our code to run about 100 times faster. Okay, in this case, you see it's more than 100 times faster. So if the code takes 20 minutes to run, it will actually be very prohibitive. And this was only, say, 200 stocks. So in our case, it's only 6 minutes, but what we're saying is that it could be a lot worse. And we can show how to profile your code and improve your system so that the code is more efficient. Well, this is so inside this paper, what we do is we just go through some ways to profile our code and see where the blockages are. So we want to see exactly where the performance issue is occurring, and we go through some ways to profile our code and inspect some lower level bytecodes and things like that. Okay, but inside that paper, we just show you how to profile the code, but we don't actually show you how to improve the code. So that would be inside the full version of the paper, which is also on the website, but that was meant for our paid readers only. So in this lecture, we're going to actually reveal the improvements that we made, and we're going to show you how to both profile and then make the changes to improve the code. So if you have seen that paper and if you have full access to the entire paper, then of course what we're going to do is very similar, but in this case, for those of you who have not seen it, who don't have access to the full paper, we're going to talk about exactly what to do inside this lecture series. Okay, so another thing is, while we can do a lot of profiling outside of the Python runtime, such as using system commands. So for example, we can do timing, like you see the paper. Let me just go back to the paper, right? We can do, you can use the system user time command, and then we can write some statistics to a text file and understand some properties of the process being ran. So for example, what's the CPU time, how many times the system had to go to the disk to load things to the RAM, how many minor page faults, context switches, and things like that. This will be presented. You can also get even more advanced statistics if you're on Linux. You get access to the perfstat tool. This will teach us. And for us, we're on the Mac, so we won't have access to this. But in general, if you have access to that tool, then you can see how many clock cycles, what are the number of instructions per cycle, how well you're using your system cache, the branch predictions and branch misses, things like that. You can see very clear details on the lower level system calls and the state and how well you're utilizing your computer's memory architecture. But because we want everyone to be able to follow along, we're not going to talk about system level commands. Instead, we're going to stay exclusively inside the Python runtime. Right, we're going to stay exclusively inside the Python runtime and see exactly how to improve our code just using Python code. Right, so let's clear all of this. This is the target we have in mind. The first tool we're going to introduce is called the C profile. Okay, the C profile is basically gives us information about the different function calls, how much time it's spent inside each call, or the total amount of time spent inside the calls, and things like that. We're just going to show exactly how to do that instead of describing it. We're just going to go ahead and show you. So in order to do that, we can actually do something like, okay, we don't want to wait another 18 minutes, so we're just going to do it for a very short problem. So okay, we just do it for 20 tickers. Okay, we're just going to optimize on a smaller set of tickers, and then later we will go back to 200 and see whether our code, how fast our code is. So let's just do it for the first two problems. And what we'll do is we do Python 3-m, then we will add this command to say that we want to profile our code, and then we'll specify an output file, and then we'll do stats.text. So this will write to a statistics file, and then we will call a Python file. Okay, so let's run this code and see what we get out of it. So the simulation took us about 2 minutes, and we have a result. Let's just take a look at it. So this, let's just copy and paste this so that we can have a reference later, right? So let's look at, so let's just create a temporary Python file. Let's create the statistics file. So we can just see the statistics file, but oh, it's a binary code. But anyway, we want to read the statistics. Let's open this. It's just a lot of gibberish. So in order to integrate the statistics, we can use a pstats module. So so if you want to know what is going on, you can Google and look for Python profilers. The statistics, the pstats module basically allows us to understand this binary statistics file, and you can see information like what is the 20 most heavily used function in terms of the call time. You can also see who calls who is called by who, and information like that. So this is very useful for us. We're just going to demonstrate how to use that. So let's just import pstats, and then let this be the statistics file, so pstats.stats, and then we have stats.text. So we're doing this statistics file. We don't want any information about the directories from which we're running our code. We want to sort the statistics by cumulative call time, and then we want to just call the 20 most pertinent problems. So let's run our statistics files, and we get an interesting, we get this output. So we can just ignore. So this is basically our entry into the Python code. So we will call main. So these 4 functions are basically not too interesting because these are our entry into the code, and you can see that this isn't. Basically, this is just your main entry into what you're typing in the first place, so we're not interested in that. You can see here right away that these already take a lot of time, and this function is, and the next most pertinent problem is this get item with a cumulative time of 58 seconds. So with a total runtime of 120 seconds, we're spending about half the time inside this function. So what is this function doing? That's what we want to ask. Right, so exactly this get item and set item function. So both of them are taking about a significant proportion of the time. So this is not very clear, right? Because we're not explicitly, we didn't have an indexing.py file, so it means this is one of our. So we're making a function call that makes a function call to this indirectly, right? So in order to understand where this is coming from, where this number of calls are coming from, what we can do is then to say we can print the number, we can print the callers, we can print the top 20 callers of dash dash get item, like this, and we'll get an output. So we're making the calls inside compute. These two functions make the calls to get item, whereas this one is probably making a implicit call. So let's just go and see what are inside this compute signal distribution and get piano stats. So that means we're making these 2 function calls exactly in these 2 places. So here, I can go to util files. So what are the function calls? So get piano stats and the get signal distribution. So what's the distributive function call that gets an item? In fact, these are all mathematical computations, so it's none of these lines, right? This will just be computation. But you can see that the thing that is being called the most is basically this accessing of cells inside new variable, of cells inside the data frame, right? So this is a data frame, and then we say give us the entry and row, date, and column close. And this is apparently done a lot of times, and for some reason, it's taking a lot of time inside. And we're calling this like hundreds of thousands of times. Inside the compute signal distribution, we also have these call to access to a cell inside. So let's just go and check. Let's go to Google and check cluster calls to .log. Right. So this question seems to be fairly similar to what we're looking for, and basically this statements are, we can see that .log is taking significantly more time compared to say these operations, which are almost 10 times faster. So it seems to me that we're using the wrong function, right? So for example, you can see .log, this is .at, and if you go to that, Automate the code, and you can see, okay, there's a documentation. So if you look at the Pandas documentation, you'll see that this is a access to scalar, whereas inside the log, it's primarily for recovering a row of columns. So you can see this the difference between these operations and when they should work. You can see, okay, the log is for index, is in position, and if you want to get scalar positions, if you only want to get scalar values, then you should not be using any of these two operations. Instead, you should be using these two operations. So okay, that's helpful. So let's, for instance, change this to add. Let's make the relevant changes. Okay, and since we're also accessing a scalar value here, we can replace with this dot add, and let's try to run the code again and see how long that takes.